Okay, welcome back to part B of 4.2 factorial notation and permutations. Um, just as a refresher from the last video, we looked at the difference between a permutation and a combination. And so important for you to know that when order matters, we're talking about permutation. And when order does not matter, we're talking about combinations. So in the last lesson, we were looking at factorial notation, what that is, how to break it down, and then how to solve equations using factorial notation. Today, we're going to look at permutations. And so a permutation, again, relates to things where order matters. So we're going to go through a series of examples, and I'm also going to show you how to do permutations using your calculator. So first example here, it says a website's access code consists of 3 digits. Knowing the 3 digits isn't enough because it has to be put in a specific order, just like with a combination lock. So the digits have to be entered in a correct order, and the order or the arrangement of the digits is important. So arrangement is a key word that often tells us that we're talking about permutations. All right, let's turn my pen on here. So if we're talking about order mattering or we're talking about an arrangement, then we're talking about permutations. So this first question here, it says, Tori can't remember the access code except that it contains digits 3, 7, and 9. So if we want to write out those combinations that we can have 3, 7, 9. We could have 3, 9, 7. We could have 7, 3, 9. We could have 7, 9, 3. We could have 9, 3, 7. And we could have 9, 7, 3. So if we look at that, there are 6 possible arrangements, so 6 possible ways that we could organize those numbers to get a code, and only one of them is correct. So order matters. Again, that's a permutation. So a keyword again for permutation is arrangement. So a permutation is an arrangement of a set of elements where the order is important. So look at another example using letters. And so it says list all the arrangements in the word ice. So if I wanted to rearrange all the letters in the word ice, I'd have ICE, IEC, CIE, CEI, EIC, and ECI. Again, there's 6 combinations. Now, a way I can look at that using fundamental counting principle. If I want to use fundamental counting principle, I'd say, well, there's 3 letters. I have 3 choices, 2 choices, and 1 choice. If I want to write this out using factorial notation, I can just write it as 3 factorial. So it says this is an example. The number of permutations of n different elements taken all at a time is n factorial. So if I have 3 elements and I'm arranging all 3 of them, or I have 10 elements and I'm arranging all 10 of them, I can use factorial notation. So here's some examples. Ralston. If we want to take the letters in the word Ralston and rearrange them to make a new word, we could write this out using fundamental counting principle. We can also write it out using factorial notation. We'd have 1, 2, 3, 4, 5, 6, 7 letters. So this would be 7 factorial and 7 factorial. If you remember from your calculator, that means you go math, left to probability, and then 4 factorial. So 7 factorial will be 50, 40. If I was looking at rearranging the letters in Kelowna, if I count those up, those are also 7. So 7 factorial. It's 5,040. If I wanted to rearrange the letters in Netflix, since we're all in isolation and that might be a popular place to check out, Netflix, there are 6 different letters. So 6 factorial. 6 factorial would be 720. Okay. Now we can also write, out some of this using permutation notation as well. So we're going to look at an example here. So if we're using the fundamental counting principle to figure out how many 3-letter arrangements can be made from the word graphite, notice this time we're not taking all of the letters, we're just taking 3 of them. So if we wanted to use fundamental counting principle, we draw out our 3 blanks, and we'd say, well, graphite has 1, 2, 3, 4, 5, 6, 7, 8 letters. So that means I have 8 choices for the first, 7 for the second, and 6 for the third. So that would give me 336 combinations. I can also look at this a different way. It says in the example above, the number of permutations of 8 elements taken 3 at a time can be written as 8p3, or you'll often hear me say 8pick3. So 8p3. Now 8p3, that's us taking 8 times 7 times 6. And if you remember from our factorial notation before, from yesterday's lesson, we have 8 times 7 times 6 times 5 factorial all over 5 factorial. So it's just another way that we can write this. We can also write 5 factorial as 8 minus 3 factorial. Well, if I put that all in my calculator, I'm going to get 336. The formula for permutations is on your formula sheet, and it's NPR equals n factorial over n minus r factorial. So the example above is just showing you how we get that formula. Really, it just matters that you're able to use this formula. Now we can do permutation notation using our calculator. And so we're going to do that right here. If you open up your calculator, to do permutations with your calculator, you have to type the n value first. So that's 8. We're going to click on the math button again and go back to where we found factorials. So again, you're hitting the 8, then math, arrow to the left, and PRB. Now we want NPR, so that's number 2. And then we type in the R value, which is 3. So 8 NPR 3. So on your calculator, it's going to look like this. 8 NPR. Now the newer calculators, it might look slightly different, but it's still going to give you the same answer. So 8 NPR 3 is going to be 336. And again, you could use the factorials to figure that out. If I were to plug this in, 8 is my n, so n factorial would be 8 factorial. My n down here is 8 minus 3 bracket factorial, which becomes 8 factorial over 5 factorial. And we already had that above. That equals 336. So yesterday I told you that 0 factorial is equal to 1. And so now that we've talked a little bit about permutations, we can use that to prove why 0 factorial is 1. Now this is just one way to prove it. There's certainly other proofs out there, but this is just one that relates to permutations. So if we replace R using the letter n in the previous formula, we get the number of permutations of n elements taken n at a time. So if I have n elements taken n at a time, that can be represented as n factorial. Now using our formula from the last page, NPR is n factorial over n minus r factorial. So if I'm using NPN, then n factorial over n minus r factorial is just n minus n factorial. So that's 0 factorial. For this to be equal to n factorial, we can only get that if 0 factorial is equal to 1. So the only way that we can get n factorial to equal n factorial is if we're dividing by 1. And so 0 factorial has to be 1. Now this isn't a full proof, this is more just using logic, but I don't want to get into the other proofs at this point. Alright, so let's take an example, or look at an example, and we're going to compare fundamental counting principle and permutations side by side. So same question, so one question, and we're going to solve it using 2 different methods. So in a certain region, vehicle license plates consist of 2 different letters followed by 4 different digits. And it says that I, O, Y, and Z are not used. And we're going to figure out how many different license plates are possible. Now we already did these questions a couple of days ago when we were talking about fundamental counting principle. We're just revisiting that example. So again, you start by drawing out your blanks. There's the 2 letters and the 4 digits. And then write out what your restrictions are. So these here have to be letters, and we're not going to use I, O, Y, or Z. And these ones over here are numbers, anything from 0 to 9. Now, it doesn't say anything in there about repetition. However, it does say right here to different letters followed by 4 different numbers. So that means no repeats. So we've got all of our criteria written out. Now we're going to actually fill in those numbers. So there's 26 letters in the alphabet. If there's 4 of them that we can't use, then that means we have 22 choices. And then our next option, because there's no repetition allowed, is 21. We start off with 10 digits from 0 to 9. We can't repeat any of them, so we've got 10 times 9 times 8 times 7. If we were to multiply that out, it would give us 2,328,480. All right, now how would this look with permutations? Well, with permutations, we're going to deal with our letters and our numbers separately. So for the letters part, we have 22 letters to choose from. Order matters, so we're using a permutation, and we want to pick 2. So we have 22 letters to pick from, and we're picking 2. For the digits, we have 10 digits to pick from, and we're picking 4. So 10 pick 4. And this would also give me 2,328,480. So how do I go about putting that in my calculator? I'm going to type in bracket 22 math over to the left, 2, close your bracket, 10 math over to the left, 2, 4, close your bracket, and we'll get 2,328,480. So it's important for you to know that in most cases, when we're talking about permutations, the fundamental counting principle can be used in place of permutations. So you might find yourself gravitating to one over the other, but it's important to know that we can use one or the other, and that's in most of the cases. So hopefully that gives you enough information about permutations. This is just an introduction. In the upcoming lessons, we're going to look at permutations with restrictions, and we're also going to look at permutations with repetition. If you notice at this point, all of the words that we've been rearranging have no repeating letters. So we're going to get into that in some upcoming lessons. All right, thanks guys. Have a great day, and we'll see you soon.